Ohio, is home to the world's largest vacuum chamber. It is 30 meters in diameter and 37 meters high, and was designed in the 1960s to test nuclear rockets in simulated spacelike conditions. No nuclear rocket has ever been fired inside. The program was cancelled before the facility was completed. But many spacecraft, from the Skylab nose cone to the airbags on Mars landers, have been tested inside this cathedral of aluminium. To my absolute delight, NASA agreed to conduct an experiment using their vacuum chamber to demonstrate precisely what motivated Einstein to his remarkable conclusion. The experiment involves pumping all the air out of the chamber and dropping a bunch of feathers and a bowling ball from a crane. Both Galileo and Newton knew the result, which is not in question. The feathers and the bowling ball both hit the ground at the same time. Newton's explanation for this striking result is as follows. The gravitational force acting on a feather is proportional to its mass. We've already seen this written down in Newton's law of gravitation. That gravitational force causes the feather to accelerate according to Newton's other equation, F equals ma. This equation says that the more massive something is, the more force has to be applied to make it accelerate. Magically, the mass that appears in F equals ma is precisely the same as the mass that appears in the law of gravitation, and so they precisely cancel each other out. In other words, the more massive something is, the stronger the gravitational force between it and the Earth, but the more massive it is, the larger this force has to be to get it moving. Everything cancels out, and so everything ends up falling at the same rate. The problem with this explanation is that nobody has ever thought of a good reason why these two masses should be the same. In physics, this is known as the equivalence principle, because gravitational mass and inertial mass are precisely equivalent to each other. Einstein's explanation for the fact that both the feathers and the bowling ball fall at the same rate in the Plum Brook vacuum chamber is radically different. Recall Einstein's happiest thought. Because for an observer falling freely from the roof of a house, there exists no gravitational field. There is no force acting on the feathers or the ball in free fall, and therefore they don't accelerate. They stay precisely where they are, at rest relative to each other. Or if you prefer, they stand still because we are always able to define ourselves as being at rest if there are no forces acting on us. But you are surely asking, how come they eventually hit the ground if they are not moving because no forces are acting on them? The answer, according to Einstein, is that the ground is accelerating up to meet them and hits them like a cricket bat. But, you must be thinking, I'm sitting on the ground now and I'm not accelerating. Oh yes, you are, and you know it because you can feel a force acting on you. It's the force exerted by the chair on which you may be sitting or the ground on which you are standing. This is obvious. If you stand up long enough, then your feet will hurt because there is a force acting on them. And if there is a force acting on them, then they are accelerating. There's no sleight of hand here. The very beautiful thing about Einstein's happiest thought is that once you know it, it's utterly obvious. Standing on the ground is hard work because it exerts a force on you. The effect is precisely the same as sitting in an accelerating car and being pushed back into your seat. You can feel the acceleration viscerally. And if you switch off your common sense for a moment, then you can feel the acceleration now. The only way you can get rid of the acceleration, momentarily, is to jump off a roof. This is wonderful reasoning, but of course it does raise the thorny question of why, if there is no such thing as gravity, the Earth orbits the Sun. Maybe Aristotle was right after all. The answer is not easy, and it took Einstein almost a decade to work out the details. The result, published in 1916, is the general theory of relativity, which is often cited as the most beautiful scientific theory of them all. General relativity is notoriously mathematically and conceptually difficult when you get into the details of making predictions that can be compared with observations. Indeed, most physics students in the UK will not meet general relativity until their final year or until they become postgraduates. But having said that, the basic idea is very simple. Einstein replaced the force of gravity with geometry, in particular, the curvature of space and time. Imagine that you are standing on the surface of the Earth at the equator with a friend. You both start walking due north, parallel to each other. As you get closer to the North Pole, you will find that you move closer together, and if you carry on all the way to the pole, you will bump into each other. If you don't know any better, then you may conclude that there is some kind of force pulling you both together. But in reality, there is no such force. Instead, the surface of the Earth is curved into a sphere, and on a sphere, lines that are parallel at the equator meet at the pole. They are called lines of longitude. This is how geometry can lead to the appearance of a force. Einstein's theory of gravity contains equations that allow us to calculate how space and time are curved by the presence of matter and energy, and how objects move across the curved space-time, just like you and your friend moving across the surface of the Earth. Space-time is often described as the fabric of the universe, which isn't a bad term. Massive objects such as stars and planets tell the fabric how to curve, and the fabric tells objects how to move. In particular, all objects follow straight-line paths across the curved space-time that are known in the jargon as geodesics. This is the general relativistic equivalent of Newton's first law of motion. Every body continues in a state of rest or uniform motion in a straight line unless acted upon by a force. Einstein's description of the Earth's orbit around the Sun is therefore quite simple. The orbit is a straight line in space-time, curved by the presence of the Sun, and the Earth follows this straight line because there are no forces acting on it to make it do otherwise. This is the opposite of the Newtonian description, which says that the Earth would fly through space in what we would intuitively call a straight line if it were not for the force of gravity acting between it and the Sun. Straight lines in curved space-time look curved to us for precisely the same reason that lines of longitude on the surface of the Earth look curved to us. The space upon which the straight lines are defined is curved. This is all well and good, but there may be a question that's been nagging away in your mind since I told you that the ground accelerated up and hit the feathers and the bowling ball at Plum Brook like a cricket bat. How could it possibly be that every piece of the Earth's surface is accelerating away from its center, and yet the Earth stays intact as a sphere with a fixed radius? The answer is that if a little piece of the Earth's surface at Plum Brook were left to its own devices, it would do precisely the same thing as the feather and the bowling ball. It would follow a straight line through space-time. These straight lines point radially inwards towards the center of the Earth. This is the state of rest, if you like, the natural trajectory that would be followed by anything. The geodesics point radially inwards because of the way that the mass of the Earth curves space-time. So a collapsing Earth would be the natural state of things without any forces acting, one in which ultimately all the matter would collapse into a little black hole. The thing that prevents this from happening is the rigidity of the matter that makes up the Earth, which ultimately has its origin in the force of electromagnetism and a quantum mechanical effect called the Pauli exclusion principle. In order to stay as a big, spherical, Earth-sized ball, a force must act on each little piece of ground, and this must cause each little piece of ground to accelerate. Every piece of big spherical things like planets must continually accelerate radially outwards to stay as they are, according to general relativity. From what I've said so far, it might seem that general relativity is simply a pleasing way of explaining why the Earth orbits the Sun and why objects all fall at the same rate in a gravitational field. General relativity is far more than that, however. Very importantly, it makes precise predictions about the behavior of certain astronomical objects that are radically different from Newton's. One of the most spectacular examples is a binary star system known rather less than poetically as PSR J0348 plus 0432. The two stars in this system are exotic astrophysical objects. One is a white dwarf, the core of a dead star held up against the force of gravity by a sea of electrons. Electrons behave according to the Pauli exclusion principle, which, roughly speaking, states that electrons resist being squashed together. This purely quantum mechanical effect can halt the collapse of a star at the end of its life, leaving a super-dense blob of matter. White dwarfs are typically between 0.6 and 1.4 times the mass of our Sun, but with a volume comparable to that of the Earth. The upper limit of the mass of a white dwarf is known as the Chandrasekhar limit, and was first calculated by the Indian astrophysicist Subrahmanyan Chandrasekhar in 1930. The calculation is a tour de force of modern physics, and relates the maximum mass of these exotic objects to 4 fundamental constants of nature: Newton's gravitational constant, Planck's constant, the speed of light, and the mass of the proton. After almost a century of astronomical observations, no white dwarf has ever been discovered that exceeds the Chandrasekhar limit. Almost all the stars in the Milky Way, including our Sun, will end their lives as white dwarfs. Only the most massive stars will produce a remnant that exceeds the Chandrasekhar limit, and the vast majority of these will produce an even more exotic object known as a neutron star. In the PSR J0348 plus 0432 system, quite wonderfully, the white dwarf has a neutron star companion, and this is what makes the system so special. If the remains of a star exceed the Chandrasekhar limit, the electrons are squashed so tightly onto the protons in the star that they can react together via the weak nuclear force to produce neutrons with the emission of a particle called a neutrino. Through this mechanism, the whole star is converted into a giant atomic nucleus. Neutrons, just like electrons, obey the Pauli exclusion principle and resist being squashed together, leading to a stable, dead star. Neutron stars can have masses several times that of our Sun, but quite astonishingly are only around 10 kilometers in diameter. They are the densest stars known. A teaspoonful of neutron star matter weighs as much as a mountain. Imagine for a moment this exotic star system. The white dwarf and neutron star are very close together. They orbit around each other at a distance of 830,000 kilometers, that's around twice the distance to the Moon, once every 2 hours and 27 minutes. That's an orbital velocity of around 2 million kilometers per hour. The neutron star is twice the mass of our Sun, around 10 kilometers in diameter, and spins on its axis 25 times a second. This is a star system of unbelievable violence. Einstein's theory of general relativity predicts that the two stars should spiral in towards each other because they lose energy by disturbing space-time itself, emitting what are known as gravitational waves. The loss of energy is minuscule, resulting in a change in orbital period of 8 millionths of a second per year. In a triumph of observational astronomy, using the giant Arecibo radio telescope in Puerto Rico, the Effelsberg telescope in Germany, and the European Southern Observatory's VLT in Chile, astronomers measured the rate of orbital decay of PSR J0348 plus 0432 in 2013 and found it to be precisely as Einstein predicted. This is quite remarkable. Einstein could never have dreamt of the existence of white dwarfs and neutron stars when he had his happiest thought in 1907. And yet by thinking carefully about falling off a roof, he was able to construct a theory of gravity that describes with absolute precision the behavior of the most exotic star system accessible to 21st century telescopes. And that, if I really need to say it, is why I love physics. Einstein's theory of general relativity has, at the time of writing, passed every precision test that scientists have been able to carry out in the century since it was first published. From the motion of feathers and bowling balls in the Earth's gravitational field to the extreme astrophysical violence of PSR J0348 plus 0432, the theory comes through with flying colours. There is rather more to Einstein's magisterial theory than the mere description of orbits, however. General relativity is fundamentally different from Newton's theory because it doesn't simply provide a model for the action of gravity. Rather, it provides an explanation for the existence of the gravitational force itself in terms of the curvature of space-time. It's worth writing down Einstein's field equations because they are, to be honest, deceptively simple. G mu nu equals 8 pi gt mu nu. Here, the right side describes the distribution of matter and energy in some region of space-time, and the left-hand side describes the shape of space-time as a result of the matter and energy distribution. To calculate the orbit of the Earth around the Sun, one would put a spherical distribution of mass with the radius of the Sun into the right-hand side of the equation, and, roughly speaking, out would pop the shape of space-time around the Sun. Given the shape of space-time, the orbit of the Earth can be calculated. It's not completely trivial to do this by any means, and the notation above hides great complexity. But the point is simply that given some distribution of matter and energy, Einstein's equations let you calculate what space-time looks like. But here is the remarkable point that draws us towards the end of our story. Einstein's equations deal with the shape of space-time, the fabric of the universe. The first thing to note is that we are dealing with space-time, not just space. Space is not a fixed arena within which things happen with a big universal clock marking some sort of cosmic time upon which everyone agrees. The fabric of the universe in Einstein's theory is a dynamical thing. Very importantly, therefore, Einstein's equations don't necessarily describe something that is static and unchanging. The second thing to note is that nowhere have we restricted the domain of Einstein's theory to the region of spacetime around a single star or even a double star system such as PSR J0348 plus 0432. Indeed, there is no suggestion in Einstein's theory that such a restriction is necessary. Einstein's equations can be applied to an unlimited region of spacetime. This implies that they can, at least in principle, be used to describe the shape and evolution of the entire universe. A day without yesterday. Storytelling is an ancient and deeply embedded human impulse. We learn, we communicate, we connect across generations through stories. We use them to explore the minutiae of human life, taking delight in the smallest things. And we tell grander tales of origins and endings. History is littered with stories about the creation of the universe. They seem as old as humanity itself. Multifarious gods, cosmic eggs, worlds emerging from chaos or order, from the waters or the sky or nothing at all. There exist as many creation myths as there are cultures. The impulse to understand the origin of the universe is clearly a powerful unifying idea, although the very existence of many different mythologies continues to be a source of division. It's an unfortunate testament to the emotional power of creation narratives that so much energy is spent arguing about old ones, rather than using the increasingly detailed observational evidence available to 21st century citizens to construct new ones. We live in a very privileged and exciting time in this sense, because observational evidence for creation stories was scant even a single lifetime ago. When my grandparents were born in Oldham at the turn of the 20th century, there was no scientific creation story. Astronomers were not even aware of a universe beyond the Milky Way, which makes it all the more remarkable that the modern scientific approach to the description of the universe emerged almost fully formed from Einstein's theory of general relativity before Edwin Hubble published the discovery of his Cepheid variable star in Andromeda and settled Shapley and Curtis's great debate. One of the beautiful things about mathematical physics is that equations contain stories. If you think of equations in terms of the nasty little things you used to solve at school on a damp autumn afternoon, then that may sound like a strange and abstract idea. But equations like Einstein's field equations are much more complex animals. Recall that Einstein's equations will tell you the shape of spacetime, given some distribution of matter and energy. That shape is known as a solution of the equations, and it is these solutions that contain the stories. The first exact solution to Einstein's field equations was discovered in 1915 by the German physicist Karl Schwarzschild. Schwarzschild used the equations to calculate the shape of spacetime around a perfectly spherical, non-rotating mass. Schwarzschild's solution can be used to describe planetary orbits around a star, but it also contains some of the most exotic ideas in modern physics. It describes what we know now as the event horizon of a black hole. The well-known tales of astronauts being spaghettified as they fall towards oblivion inside a supermassive collapsed star are to be found in Schwarzschild's solution. The calculation was a remarkable achievement, not least because Schwarzschild completed it whilst serving in the German army at the Russian front. Shortly afterwards, the 42-year-old physicist died of a disease contracted in the trenches. The most remarkable stories waiting to be found inside Einstein's equations reveal themselves when we take an audacious and seemingly reckless leap. Instead of confining ourselves to describing the spacetime around spherical blobs of matter, why not think a little bigger? Why not try to use Einstein's equations to tell us about all of space-time? Why can't we apply general relativity to the entire universe? Einstein noticed this as a possibility very early in the development of his theory, and in 1917 he published a paper entitled Cosmological Considerations of the General Theory of Relativity. It's a big step, of course, from thinking about someone falling off a roof to telling the story of the universe, and Einstein appears to have been uncharacteristically wobbly. In a letter to his friend Paul Ehrenfest, a few days before he presented his paper to the Prussian Academy, he wrote, "I have, again, perpetrated something about gravitation theory, which somewhat exposes me to the danger of being confined in a madhouse." The universe modelled in Einstein's 1917 paper is not the one we inhabit, but the paper is of interest for the introduction of what Einstein later came to view as a mistake. Einstein tried to find a solution to his equations that would describe a finite universe, populated by a uniform distribution of matter and stable against gravitational collapse. At the time, this was a reasonable thing to do because astronomers knew of only a single galaxy, the Milky Way, and the stars did not appear to be collapsing inwards towards each other. Einstein also seems to have had a particular story in mind. He felt that an eternal universe was more elegant than one that had a beginning, which left open the thorny question of a creator. He discovered, however, that general relativity does not allow for a universe with stars, planets, and galaxies to be eternal. Instead, his solution told the story of an unstable universe that would collapse inwards. Einstein tried to solve this unfortunate problem by adding a new term in his equations known as the cosmological constant. This extra term can act as a repulsive force, which Einstein adjusted to resist the tendency of his model universe to collapse under its own gravity. Later, he is famously said to have remarked to his friend George Gamow that the cosmological constant was his biggest blunder. As physicists began to search for solutions to Einstein's equations, more and more possible universes were discovered. None, with the exception of Einstein's universe and a universe without matter and dominated by a positive cosmological constant, discovered in 1917 by Willem de Sitter, was static. We will return to de Sitter's universe in a moment, but in every other case, Einstein's equations seem to imply continual evolution, whereas Einstein himself felt that the universe should be unchanging and eternal. As more physicists worked with the equations, things only got worse for Einstein's static eternal universe. The first exact cosmological solution of Einstein's equations for a realistic universe filled with galaxies was discovered by Russian physicist Alexander Friedmann in 1922. He reached his result by assuming something that takes us all the way back to the beginning of this chapter, a Copernican universe, in the sense that nowhere in space is special. This is known as the assumption of homogeneity and isotropy, and it corresponds to solving Einstein's equations with a completely uniform matter distribution. This may seem to be a gross oversimplification, and in the early 1920s, the extent to which this assumption agreed with the observational evidence, a universe seemingly containing just a single galaxy, was tenuous. From a theoretical perspective, however, Friedmann's assumption makes perfect sense. It's the simplest assumption one can make, and it makes it relatively easy to do the sums. So relatively easy, in fact, that Friedmann's work was replicated and extended quite independently by a Belgian mathematician and priest named Georges Lemaitre. Lemaitre planted his flag firmly in the no-man's land between religion and science, a strip of intellectual land occupied, whether we like it or not, by cosmology. A student of Harlow Shapley, this deeply religious man never saw a conflict between these two very different modes of human thought. He embodies the much debated and criticized modern notion, introduced by the evolutionary biologist Stephen Jay Gould, that science and religion are non-overlapping magisteria, asking the same questions but operating within separate domains. My view is that this is far too simplistic a position to take. Questions concerning the origin of the physical universe are of the same character as questions about the nature of the gravitational force or the behavior of subatomic particles, and answers will surely be found by employing the methodology of science. Having said that, I am willing to recognize that romance or wonder or whatever the term is for that deep feeling of awe when contemplating the universe in all its immensity is a central component of both religious and scientific experience. And perhaps there is room for both in providing the inspiration for the exploration of nature. At least this is what Lemaitre felt, and he used his twin perspectives as a guide on his intellectual journey through the cosmos throughout his distinguished career. Ordained a priest in 1923 while studying at the Catholic University in Louvain, Lemaitre studied physics and mathematics alongside some of the great physicists and astronomers of the time, including Arthur Eddington and Harlow Shapley, from the University of Cambridge to Harvard and MIT, before returning to Belgium in 1925 to work with Einstein's general relativity. Lemaitre never met Alexander Friedmann, who died from typhoid in 1925. They never spoke or corresponded, and Lemaitre was almost certainly unaware of the obscure paper Friedmann had published describing a dynamic and changing universe. He followed the same intellectual path, however, assuming an isotropic and homogeneous distribution of matter in the cosmos, and searching for solutions to Einstein's equations that described the story of this smooth and uniform universe. And of course, he came to the same conclusion. Such a universe cannot be static. It must either expand or contract. Lemaitre met Einstein at the 1927 Solvay conference in Brussels and told him of his conclusions. "Your calculations are correct, but your physics insight is abominable," snapped the great man. Einstein was wrong. By 1931, Lemaitre was writing papers containing wonderfully vivid phrases and making clear his view that Einstein's theory requires a moment of creation, a Big Bang. He writes of a day without yesterday, and of the universe emerging from a primeval atom. In 1934, the Princeton physicist Howard Percy Robertson catalogued all of the possible solutions to Einstein's equations given a uniform distribution of matter throughout the cosmos, a perfect Copernican principle according to which no place in the cosmos is special or significant. The models containing matter tend to describe either an expanding or contracting universe, and therefore suggest a quite wonderful thing. There may have been a day without a yesterday. Einstein's equations contain within them a scientific creation story, even though their author himself resisted it. The story of Einstein's theory of general relativity and its subsequent application to the whole universe delivers a compelling narrative illustrating the power of physics. The theory, inspired by thinking about a man falling off a roof, predicts that there was a moment of creation. No experimental measurements are required, and no observations need be made other than that things fall at the same rate in a gravitational field. There are multiple layers of irony here. The idea that such progress towards answering the most profound questions about our origins can be made by thinking alone is almost Aristotelian, a partial throwback to the lofty authority of the classical world that Bruno, Copernicus and Galileo did so much to overturn. That the equations seem to describe a universe with a necessary moment of creation, lending support, at least in Lemaitre's eyes, to the notion of a creator, would also appear to bring us full circle and back to Borman, Lovell and Anders and the creation stories of old. Indeed, Pope Pius XII, on hearing about the new cosmology, said, "True science to an ever-increasing degree discovers God, as though God was waiting behind each door opened by science." Einstein, to his deep chagrin, having thrown a blanket of rational thought across a landscape of mythology, appeared to have replaced one creation story with another. To finish the story of our magnificent relegation, let me briefly address these points. The theoretical prediction of an expanding universe does of course require experimental verification, and this came rapidly. On the 15th of March 1929, Edwin Hubble published a paper entitled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae, in which he reported his observation that all galaxies beyond our local group are rushing away from us. Moreover, the more distant the galaxy, the higher its speed of recession. This is precisely what an expanding universe, as predicted by Einstein's theory, should look like. In 1948, Alpha, Beta and Gamow published a famous paper with the coolest author list in the history of physics, which showed how the observed abundance of light chemical elements in the universe could be calculated assuming a very hot, dense phase in the early history of the universe. Modern calculations of these abundances are extremely precise and agree perfectly with astronomical observations. Perhaps most compellingly of all, the afterglow of the Big Bang, known as the cosmic microwave background radiation, also predicted by Alpha and Hermann in 1948, was discovered by Penzias and Wilson in 1964. We will have much to say about the cosmic microwave background in the following chapters. For now, it is sufficient to say that the discovery that the universe is still glowing at a temperature of 2.7 degrees above absolute zero was the final evidence that convinced even the most skeptical scientists that the Big Bang theory was the most compelling model for the evolution of the universe. What, though, of the thorny question of the cause of the Big Bang itself? What was the origin of Lemaitre's primeval atom? Did God really do it? The standard Big Bang cosmology of the 20th century has no answer to this question, but 21st century cosmology does. We will address the current scientific understanding of what happened before the Big Bang later on, but let me offer a tantalizing hint here. It is now thought that before the Big Bang, the universe underwent a period of exponential expansion known as inflation. In this time, the universe behaved in accord with de Sitter's matterless solution to Einstein's equations discovered in 1917. This period of rapid expansion gave us the homogeneous and isotropic distribution of matter we see today on large distance scales, which is the reason why Friedmann and Lemaitre's simple Copernican assumptions lead to a description of the evolution of the universe after the Big Bang that fits observational data perfectly. There are no special places in the universe because the early inflationary expansion smoothed everything out. When inflation stopped, the energy contained within the field that drove it was dumped back into the universe, creating all the matter and radiation we observe today. Small fluctuations in the inflation field seeded the formation of the galaxies, uniformly distributed across the sky in their billions, each containing countless worlds, quite possibly without end beyond the visible horizon. In the words of Georges Lemaitre, standing on a well-cooled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the worlds. Our cinder is not special. It is insignificant in size, one world amongst billions in one galaxy amongst trillions. But it has been a tremendous ascent into insignificance, because by the virtuous combination of observation and thought, we have been able to discover our place. How Giordano Bruno would have loved what we found. Chapter 2. Are we alone? Sometimes I think we are alone in the universe, and sometimes I think we're not. In either case, the idea is quite staggering. Arthur C. Clarke. Science, fact or fiction? There are questions to which knowing the answers would have a profound cultural effect. The question of our solitude is one. Are we alone in the universe? Yes or no? One of these is true. The question as posed isn't a good one, however, because it is impossible to answer in the affirmative. We have no chance, even in principle, of exploring the entire universe, which extends way beyond the visible horizon 46 billion light-years away. The answer can never therefore be yes with certainty. Indeed, if the universe is infinite in extent, we have our answer. No, we are not alone. The laws of nature self-evidently allow life to exist, and no matter how improbable, life must have arisen an infinite number of times. In itself, this is quite a challenging statement, and we will explore it in more detail later on. But this isn't really what most of us want to know. I've always been interested in aliens, the ones that fly spaceships around, and I want to talk to one. On a winter afternoon in 1977, I stood in a queue that went around 3 sides of the Odeon Cinema in Oldham with my dad, shuffling through half-frozen puddles to see Star Wars, and spent the next decade building Millennium Falcons out of Lego. At some point in 1979, I picked up a magazine about Alien and moved on to Nostromo, which required more bricks. To my delight, I saw Alien when I was 11 years old at Friday Evening Film Society at school, and it didn't put me off. I just realized I really liked the spaceships and didn't care much about the organic stuff. Everyone should see Alien at 11. To hell with the ratings. Terror, technology, and Sigourney Weaver are good for the soul. Science fiction was a natural home for my imagination. I'd been interested in astronomy for a while. I'm not sure why, but the study of the stars seemed clean and precise and romantic. Something done on cold nights before Christmas with mittens and imagination. Star Wars, Star Trek, Alien, Arthur C. Clarke and Isaac Asimov were merged seamlessly with Patrick Moore, Carl Sagan and James Burke, and they remain so. Fact and fiction are inseparable in dreams. The superficially orthogonal desires to do science and to imagine distant worlds are closely related, shadows cast by different lights. So the question, are we alone in the universe, might make good science fiction, but it is not well posed in a scientific sense because the universe is too big for us to explore in its entirety. If we restrict the domain of the question, however, we can address it scientifically. Are we alone in the solar system is a question we are actively seeking to answer with Mars rovers and future missions to the moons of Jupiter and Saturn, where the conditions necessary for life may be present on multiple worlds. But even here, the use of the word alone in the question is problematic. Would we be alone if the universe were full of microbes? Would you feel alone, stranded in a deep cave with no means of escape and a billion bacteria for company? If not being alone means having intelligent beings to communicate with, sophisticated creatures that build civilizations, have feelings, do science and respond emotionally to the universe, then we have our answer in the solar system. Yes, Earth is the only world that is home to a civilization, and we are alone. How far might we reasonably expect to extend the domain of our question beyond the solar system? I find it impossible to believe that we'll ever explore the universe beyond our own galaxy. The distance between the Milky Way and our nearest neighbour Andromeda is over 2 million light-years, and that seems to me to be an unbridgeable distance, at least given the known laws of physics. But that still leaves an island of several 100 billion stars, 100,000 light-years across. We will therefore rephrase our question so that we have a chance of interrogating it in a scientific way, and ask, are we the only intelligent civilization in the Milky Way galaxy? If the answer is yes, then we are in the cosmic equivalent of an inescapable cave, and that would have made my 11-year-old self gazing up at a dark sky of infinite possibilities extremely sad. There may be others out there amongst the distant galaxies, but we'll never know. If the answer is no, on the other hand, this would have profound consequences. Aliens would exist in a truly science fiction sense. Beings with spacecraft, culture, religion, art, beliefs, hopes and dreams out there amongst the stars, waiting for us to speak with them. What are the chances of that? We don't know. But at least we have posed a question that can be explored scientifically. How many intelligent civilizations are there likely to be in the Milky Way, given the available evidence today? The first aliens. On the 24th of June 1947, Ken Arnold, an amateur pilot from Scobie, Montana, was flying over Mount Rainier, one of the most dangerous volcanoes in the world. Arnold was an experienced pilot with thousands of flying hours, and this implied he was a trustworthy observer. On returning to the airfield, he claimed to have seen 9 objects flying in the mountain skies, describing them as flat like a pie pan and like a big flat disc. He estimated that the discs were flying in formation at speeds of up to 1,920 kilometers per hour. The press jumped on the story, coining the term flying saucer, and within weeks, hundreds of similar sightings were reported from all over the world. On the 4th of July, a United Airlines crew reported seeing another formation of 9 discs over the skies of Idaho, And 4 days later, the mother of all UFO stories exploded at Roswell, New Mexico, with the confirmation and then rapid retraction by the United States Air Force of a recovered flying disc. An alien craft crash-landed on Earth. I'll put my cards on the table here. I believe in UFOs. That is to say, I believe that there have been sightings of flying things in the sky that the observers were unable to identify, some of which were objects. But I do not believe for a moment that these were spacecraft flown by aliens. Occam's razor is an important tool in science. It shouldn't be oversold. Nature can be complex and bizarre. But as a rule of thumb, it is most sensible to adopt the simplest explanation for an observation until the evidence overwhelms it. My favourite response to the criticism that dismissing the possibility of alien visitations to Earth is unscientific was provided by physicist and Nobel laureate Richard Feynman in his Messenger lectures at Cornell University in 1964. Some years ago, I had a conversation with a layman about flying saucers. Because I am scientific, I know all about flying saucers. I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? No, I said, I can't prove it's impossible. It's just very unlikely. At that he said, you are very unscientific. If you can't prove it impossible, then how can you say that it's unlikely? But that is the way that is scientific. It is scientific only to say what is more likely and what less likely, and not to be proving all the time the possible and impossible. To define what I mean, I might have said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the results of the known irrational characteristics of terrestrial intelligence than of the unknown rational efforts of extraterrestrial intelligence. It is just more likely. That is all. Irrespective of the veracity of the stories of mutilated cows, crop circles, and violated Midwesterners at the hands of these alien visitors, the cultural impact of these early sightings was very real. America quickly entered into a media-fueled love affair with alien invaders in shiny discs, brandishing anal probes. Why didn't they use MRI scanners, a non-Freudian would surely ask. Of all the hundreds of thousands of references to flying saucers that began to appear in the media, a cartoon by Alan Dunn, published in the New Yorker magazine on the 20th of May 1950, found its way into the lunchtime conversation of a group of scientists at the Los Alamos National Laboratory in New Mexico. Enrico Fermi was one of the greatest 20th century physicists. Italian by birth, he conducted his most acclaimed work in the United States, having left his native country with his Jewish wife Laura in 1938 as Mussolini's grip tightened. Fermi worked on the Manhattan Project throughout World War II, first at Los Alamos and then at the University of Chicago, where he was responsible for Chicago Pile 1, the world's first nuclear reactor. In a squash court underneath a disused sports stadium in December 1942, Fermi oversaw the first man-made nuclear chain reaction, paving the way for the Hiroshima and Nagasaki bombs. After the war, Fermi settled as a professor in Chicago, but he often visited Los Alamos. During one of these visits in the summer of 1950, Fermi settled down for lunch with a group of colleagues including Edward Teller, the architect of the hydrogen bomb, and fellow Manhattan Project alumni Herbert York and Emil Konopinski. At some point, talk turned to the recent reports of UFO sightings and the New Yorker cartoon, stimulating Fermi to ask a simple question that turned a trivial conversation into a serious discussion. Where are they? Fermi's question is a powerful and challenging one that deserves an answer. It has become known as the Fermi paradox. There are hundreds of billions of star systems in the Milky Way galaxy. Our solar system is around 4.6 billion years old, but the galaxy is almost as old as the universe. If we assume life is relatively common, and on at least some of these planets intelligent civilizations arose, it follows that there should exist civilizations far in advance of our own, somewhere in the galaxy. Why? Our civilization has existed for around 10,000 years, and we've had access to modern technology for a few hundred. Our species, Homo sapiens, has existed for 250,000 years or so. This is a blink of an eye in comparison to the age of the Milky Way. So if we assume we are not the only civilization in the galaxy, then at least a few others must have arisen billions of years ahead of us. But where are they? The distances are not so vast that we cannot imagine travelling between star systems in principle. It took us less than a single human lifetime to go from the Wright brothers to the moon. What might we imagine doing in the next 100 years, or 1,000 years, or 10,000 years, or 10 million years? Even with rocketry technology as currently imagined, we could colonize the entire galaxy on million-year timescales. The Fermi paradox simply boils down to the question of why nobody has done this, given so many billions of worlds and so many billions of years. It is a very good question. Listen very carefully. For 3 days in 1924, William F. Friedman had a very important job. As chief cryptographer to the US Army, Friedman was used to dealing with national security responsibilities. But from the 21st to the 23rd of August, he was asked to search for an unusual message. On these dates, Mars and Earth came within 56 million kilometers of each other, the closest the two planets had been since 1845, and they would not be so close again until August 2003. This offered the best opportunity since the invention of radio to listen in on the neighbours. To make the most of the planetary alignment, scientists at the United States Naval Observatory decided to conduct an ambitious experiment. Coordinated across the United States, they conducted a National Radio Silence Day, with every radio in the country quietened for 5 minutes on the hour every hour, across a 36-hour period. With this unprecedented radio silence, and a specially designed radio receiver mounted on an airship, the idea was to make the most of the Martian flyby and listen in for messages, intentional or otherwise, from the Red Planet. Conspiracy theories notwithstanding, William F. Friedman didn't decipher the first message from an alien intelligence, and the American public soon tired of the disruption to their news bulletins, but the principle of the experiment was sound. The idea that we might listen in to aliens had first been proposed 30 years earlier by the physicist and engineer Nikola Tesla. Tesla suggested that a version of his wireless electrical transmission system could be used to contact beings from Mars, and subsequently presented evidence of first contact. He wasn't right, but in 1896, 1 year before the publication of War of the Worlds, it was certainly a plausible claim. Tesla wasn't alone. Other luminaries of the time shared his optimism, including the pioneer of long-distance radio transmission, Guglielmo Marconi, who believed that listening to the neighbours would become a routine part of modern communication. By 1921, Marconi was publicly stating that he had intercepted wireless messages from Mars, and if only the codes could be deciphered, conversation would soon begin. The failure of the National Radio Silence Day brought a temporary halt to the organised search for extraterrestrial signals, and the idea dropped out of scientific fashion until the post-war flying saucer boom. One of the first scientists to make the search for ET scientifically acceptable again was Philip Morrison, a contemporary and colleague of Fermi. It's not known whether they discussed the Fermi paradox directly, but the idea of answering it certainly played on Morrison's mind throughout the 1950s. At the end of the decade, Morrison published a famous and influential paper with another of Fermi's collaborators, Giuseppe Cocconi, laying out the principles of using radio telescopes to listen for signals. Searching for Interstellar Communications was published in the prestigious journal Nature, and proposed a systematic search of the nearest star systems on a very specific radio frequency, the so-called 21-centimeter hydrogen line. Hydrogen atoms consist of two particles, a single proton bound to a single electron. Protons and electrons have a property called spin, which for these particular particles, known as spin-half fermions, named after Enrico Fermi himself, can take only one of two values, often called spin-up and spin-down. There are therefore only two possible configurations of the spins in a hydrogen atom. The spins can be parallel to each other, both up or both down, or anti-parallel, one up and one down. It turns out that the parallel case has slightly more energy than the anti-parallel case, and when the spin configuration flips from parallel to anti-parallel, This extra energy is carried away as a photon of light with a wavelength of 21 centimeters. Morrison and Cocconi chose the hydrogen line because it's a frequency that any technological civilization interested in astronomy will be tuned into. Hydrogen is the most abundant element in the universe, and hydrogen atoms emit radio waves at precisely this frequency. If we could see these wavelengths with our eyes, the sky would be aglow, and this is why astronomers tune their radio telescopes to the 21 centimeter line to map the distribution of dust and gas in our galaxy and beyond. If a technological civilization wants to be heard, then under the assumption that anyone with any sense does radio astronomy, the 21 centimeter line would be the most obvious choice for a message. Morrison and Cocconi's paper inspired the birth of one of the most widely debated and controversial astronomical projects of modern times. Within a year of its publication, the 85-foot radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, was pointing towards two nearby stars, Tau Ceti and Epsilon Eridani, listening in to the 21 centimeter hydrogen line for any signs of unnatural order in the signals from the stars. The project, known as OSMA, after a character from L. Frank Baum's Land of Oz, was the brainchild of Frank Drake, a young astronomer from Cornell University. Drake chose Tau Ceti and Epsilon Eridani as the first target star systems because of the stars' similarity to our own Sun and their proximity, just 10 and 12 light-years away from Earth. In 1960, Drake had no idea if these stars harbored planetary systems because no planets had been detected outside our solar system at that time. We now know that Drake's guess was a good one. Tau Ceti is thought to have 5 planets orbiting the star, with one of them in the habitable zone. Epsilon Eridani is also thought to have at least one gas giant planet with an orbital period of around 7 years. After 150 hours of observation, Drake heard nothing. But for him, this was the beginning of a lifetime dedicated to the search for extraterrestrial intelligence, a search commonly known by its acronym, SETI. Today, SETI is a global scientific effort, analyzing data from telescopes used primarily for radio astronomy. The organization also has a dedicated collection of telescopes designed specifically to detect signals from extraterrestrial civilizations at the Hat Creek Radio Observatory near San Francisco. The Allen Array, named after Microsoft founder Paul Allen, who donated over $30 million to fund the construction of the project, consists of 42 radio antennae able to scan large areas of the sky at multiple radio frequencies, including the 21 centimeter hydrogen line. If there are any civilizations making a serious attempt to contact us with technology at least as advanced as our own within 1,000 light years, the Allen Array will hear them. In the early 1960s, the scientific community was skeptical about such endeavors, and Frank Drake was perceived as a maverick. It's important to be skeptical in science, but as Fermi understood, a back-of-the-envelope calculation with some plausible assumptions suggests that the search for ET may not be futile. Indeed, the alternative view that our civilization is unique or extremely rare in a galaxy of 100 billion suns appears outrageously solipsistic, and the skeptical finger might as easily be pointed at the cynics. There was, however, a handful of scientists who understood the importance of asking big questions, and together with Peter Pearman, a senior scientist at America's prestigious National Academy of Sciences, Drake organized the first SETI conference in November 1961. The Green Bank meeting was small, but the list of attendees, who named themselves the Order of the Dolphin, was impressive. Philip Morrison was there, as was his co-author of the seminal 1959 Nature paper, Giuseppe Cocconi. I have a professional connection with Cocconi, who was a noted particle physicist and director of the Proton Synchrotron Accelerator at CERN in Geneva. Cocconi was instrumental in discovering early experimental evidence for the Pomeron, an object in particle physics known as a Regge trajectory that I have spent most of my career studying. The eminent, highly respected astronomer Otto Struve also attended. Struve publicly stated his belief in the existence of intelligent extraterrestrial life, perhaps because he had recently suggested a method for detecting alien planets outside our solar system. Nobel laureate Melvin Calvin, most famous for his work on photosynthesis, was present, along with future Hewlett-Packard Vice President for R&D Barney Oliver, astronomer Su-Shu Huang, communications specialist Dana Atchley, and the colourful neuroscientist and dolphin researcher John Lilly. The most junior attendee was a 27-year-old postdoc called Carl Sagan. I would love to have been there, although I'd have spent the whole time chatting with Cocconi about Pomerans. In preparation for the meeting, Drake drew up an agenda designed to stimulate a structured conversation amongst the group. If the search for intelligent extraterrestrial life was to be taken seriously, it was clear in Drake's mind that the discussion should be rigorous and provide a framework for future research. The way to do that is to address the problem quantitatively rather than qualitatively, to break it down into a series of probabilities that can be estimated, at least in principle, using observational data. Drake focused on a well-defined question, the one we discussed above. How many intelligent civilizations exist in the Milky Way galaxy that we could, in principle, communicate with? Drake's brilliant insight was to express this in terms of a simple equation containing a series of probabilities. What is the fraction of stars in the galaxy that have planets? What is the average number of planets around a star that could support life? What is the fraction of those planets on which life begins? What is the probability that, given the emergence of simple life, intelligent life evolves? Given intelligence, how likely is it that the intelligent beings build radio telescopes and are therefore capable of communicating with us? Multiply all those probabilities together and multiply by the number of stars in the Milky Way, and you get a number. The number of intelligent civilizations that have ever existed in the Milky Way. This isn't all Drake did, however, because he was interested in the number of civilizations that we might be able to speak to now. And that requires the addition of a rather thought-provoking term: the average lifetime of civilizations from the moment they develop the technology to communicate. If a civilization arose 1 billion years ago and vanished shortly afterwards, then we would never be able to talk to them. The question of the lifetime of a civilization may have been more vivid in the early 1960s than it is today. The Manhattan Project had been the training ground for many of the great physicists, and the Cuban Missile Crisis was less than a year away, propelling the world, in Soviet Premier Khrushchev's words to President Kennedy, towards the abyss of a world nuclear missile war. To me, and to the participants at the Green Bank Conference, the idea that a civilization might destroy itself is both ludicrous and likely. We are pathetically inadequate at long-term planning, idiotically primitive in our destructive urges, and pathologically incapable of simply getting along. More of this later. Putting the lifetime term into the equation was therefore scientifically valid and a political masterstroke. Merely confronting the question should give us pause for thought at the very least. To complete the equation with the lifetime term included, recall that it should give the number of currently contactable civilizations in the Milky Way. A little thought will convince you that the whole lot must be multiplied by the current rate of star formation in the galaxy. That might not be immediately obvious, but I have confidence you can demonstrate to yourself that it's the correct thing to do. Homework is good. The completed equation, which is known as the Drake equation, is as follows. N equals R star times Fs times Fp times Ne times Fl times Fi times Fc times L, where N is the number of civilizations in our galaxy with which radio communication might be possible, i.e. which are on our current past light cone. R star is the average rate of star formation in our galaxy. Fp is the fraction of those stars that have planets. Ne is the average number of planets that can potentially support life per star that has planets. Fl is the fraction of planets that could support life that actually develop life at some point. Fi is the fraction of planets with life that actually go on to develop intelligent life, civilizations. Fc is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And L is the length of time for which such civilizations release detectable signals into space. When Drake wrote down his equation, only our star was known with precision. Star formation had been closely studied in parts of our galaxy, and the data suggested a value of around 1 new star per year. The rest of the terms were unknown in the 1960s, and we will spend the majority of this chapter exploring them, given over 50 years of astronomical and biological research. Despite the lack of experimental data, however, the Green Bank participants spent the meeting debating each one of the terms in the Drake equation. This is the power of Drake's formulation. It's not yet possible to make a measurement of the fraction of planets on which life emerges with any sort of precision. But it is possible to look at the experience we have on Earth, and increasingly in the wider solar system, and make an informed guess. The probability of the emergence of intelligence given simple life is also a difficult question, but we do know that it took over 3 billion years on Earth, and that may give us a clue. Drake's equation is valuable, therefore, because it provides a framework for discussion and debate, focuses the mind, and suggests a direction for future research, just as Drake intended. The Green Bank meeting did produce a consensus number, based on the not inconsiderable expertise of the participants. There are of the order of 10,000 civilizations present now in the Milky Way, with whom we could communicate if we had enough radio telescopes and the will to conduct a systematic search. Interestingly, Philip Morrison, veteran of the Manhattan Project, felt that the lifetime of technological civilizations may be so short that this number could well be 0, although he observed that, if we never search, the chance of success is 0. I had the privilege of meeting Frank Drake during the filming of Human Universe. In my view, he is one of the greatest living astronomers. Frank collects and cultivates orchids, and by complete coincidence I arrived at his house when his Stanhopea orchid was flowering. These delicate and complex flowers bloom for only 2 days every year, and the chance of seeing one on a random visit is therefore small. Frank turned to me and said, "Well, so it is with SETI. We've learned that we must search over and over and over through the years until we are in the right place at the right time to make the discovery. There is hope in its name, and there is nothing wrong at all with admitting a dash of hope." Throughout the 1960s and 1970s, SETI projects both big and small continued to develop across the planet. Soviet scientists joined their American contemporaries in pointing radio receivers to the sky in the hope of detecting a signal in the noise. NASA considered funding Project Cyclops, a $10 billion super array of 1,500 dishes that could listen for signals originating up to 1,000 light-years from Earth. It never progressed beyond the planning stage, but the scale of the project demonstrates that SETI was considered to be a serious scientific endeavor. By the mid-1970s, various projects had come and gone, but none had detected the faintest hint of a significant signal. This failure, combined with a lack of progress in pinning down any of the terms in the Drake equation, it was not even certain that planets existed in large numbers beyond our solar system, made the search look increasingly futile. Not only was there a deafening silence, no one had much idea where to look or how hard to listen. NASA didn't lose faith, however, and in 1973, Ohio University's 10-year-old Big Ear telescope was optimized for a SETI survey and began taking data. 4 years later, on the 18th of August 1977, Jerry R. Amon, then a volunteer at the Big Ear, received a knock on the door of his house. It was a Thursday morning, and as usual, standing at the door was a technician carrying reams of paper printouts. This was an age when a state-of-the-art hard disk could hold only a couple of megabytes, and every few days someone had to visit the telescope, print out the data, and wipe the disks clean. Amon put the 3 days' worth of printed data onto his kitchen table and began searching. He was confronted with dozens of pages covered in hundreds of letters and numbers. The list of numbers and letters depicts the strength of the signal hitting the telescope at different times. A space denotes low intensity, and higher intensities are registered as numbers from 0 to 9. For stronger signals still, letters between A and Z are used. Most of the data the Big Ear recorded contained no letters. A stream of 1s and 2s signified sweeps across the general radio hiss of the sky. That morning, however, Amon stumbled across something different. At approximately 10:16 p.m. Eastern Standard Time on the 15th of August, a radio pulse of extreme intensity entered the antennae, recorded with the alphanumeric code 6EQUJ5. The signal lasted for 72 seconds, precisely the length of time a transmission of distant origin would register as the rotation of the Earth swept the telescope past the source. This is extremely important. If the signal had been caused by some kind of Earth-based interference, it would be highly unlikely to rise and fall in this manner, precisely and coincidentally simulating the rotation of the Earth and the telescope's field of view on the sky. The peak was marked by the letter U, the strongest signal ever recorded by the Big Ear, denoting an intensity over 30 times that of the background emission of the galaxy. Equally strangely, the signal had a wavelength of 21 centimeters, the hydrogen line favoured by Morrison and Cocconi in their 1959 Nature paper. A smoking gun for extraterrestrial communication. With a now famous flourish, Eamon circled the 6 characters and scribbled "Wow" on the printout. He then continued as a research scientist should, and looked to see if it happened again. He flicked through page after page, but the event of 10:16 p.m. on the 15th of August was a solitary blip in the background noise. This presented a problem, because it should have happened again. The Big Ear telescope scans each part of the sky twice, separated by 3 minutes, so there should have been a similar wow signal in the data 3 minutes afterwards. None was present. This doesn't rule out an intelligent extraterrestrial origin. Perhaps ET just turned the transmitter off a minute or so after it was first detected. Who knows? The origin of the wow signal was narrowed down to a point in the sky in the direction of the constellation Sagittarius. Tau Sagittarii, a stable orange star twice the mass of our Sun and around 122 light-years away, is the closest bright star to the source. Since August 1977, multiple attempts have been made to recover the signal using the world's most sensitive radio telescopes. Many hours have been spent listening, but nothing unusual has ever been detected again. Today, over 35 years later, there is no satisfactory explanation. But no serious scientist, no matter how embedded in SETI, would claim it as definitive evidence of intelligent extraterrestrial communication. Scientific results have to be repeatable, and the observation has never been repeated. For the moment, the wow signal remains an interesting anomaly in an otherwise silent sky. It is the stuff of dreams, the faintest of whispers in a great silence. The Golden Voyage. 2 days after Jerry Eamon spotted the wow signal, the human race responded with a long-planned contribution to the interstellar conversation. In an explosive, serendipitous moment, the Voyager 2 spacecraft blasted into the sky above Space Launch Complex 41 at Kennedy Space Center, followed 2 weeks later by its twin Voyager 1. The Voyager missions were designed to take advantage of a rare planetary alignment to study the outer solar system gas giants Jupiter, Saturn, Uranus and Neptune. I remember the launch. I'd collected a series of PG Tips T-cards called The Race into Space, in which the Grand Tour mission was described as the most ambitious unmanned space project known. Using the newly proposed gravity assist, a spacecraft could accelerate around Jupiter, Saturn and Uranus to encounter Neptune only a decade from launch. The Voyagers delivered, I suspect, way beyond their designers' wildest dreams, returning the first detailed pictures of the esoteric moons of Jupiter and Saturn, and in the case of Voyager 2, sweeping onwards to become the only spacecraft to date to visit Uranus and Neptune, where it photographed the distant ice moon Triton in the summer of 1989. At the time of writing, on the 8th of July 2014, Voyager 1 is the most distant man-made object, at over 127 astronomical units from Earth, so distant that radio waves take over 17.5 hours to reach it. This puts Voyager 1 at the very edge of the solar system, on its way into interstellar space. The bus-sized spacecraft has enough electrical power to continue to communicate with its home world until around 2020, at which point it will fall silent. In 40,000 years, it will drift within 1.6 light-years of the red dwarf star Gliese 445 in the constellation of Camelopardalis. Voyager 2 will reach Sirius, the brightest star in the night sky, in 296,000 years. The Voyagers are accompanied on their lonely flights out of our solar system by a dream, an unusually sentimental and hopeful afterthought to a scientific mission bolted to their sides almost 40 years ago. The Voyager Golden Record is our message in a bottle, an old-fashioned phonograph record constructed of gold-plated copper floating through the universe. It contains what some would term a surreal mixture of sound recordings, images, and information. It was designed to provide an alien civilization with information about who we are, what we know, and what our planet is like. There are 116 images on the disk. The first 30 or so are scientific, illustrating our solar system, our home world, the structure of DNA, the anatomy of our bodies, our reproduction, and our birth. Anatomy takes up more room than any other subject, perhaps reflecting our own fascination with what aliens might look like. In the most magnificently colloquial and futile gesture towards the aliens' moral sensibilities, no nudity was allowed. I find it hard enough to imagine the inner workings of alien brains, but I cannot begin to fathom what it must be like inside the mind of a person who raised such an objection to the depiction of the human body. How do these beings reproduce? Perhaps they use those 10 dangly things on the ends of their arms. Disgusting! The illustrations go on to detail our planet's landscapes and the variety of life on Earth, before dedicating 50 images to our lives and the civilization we've constructed, from the Great Wall of China to a supermarket. Finally, there are images of the scientific instruments we have used to explore the universe, from microscopes to telescopes, including the Titan rocket that launched the Voyagers into space. Chosen by a committee chaired by Carl Sagan, the disc also contains music and sounds, including human greetings in 55 languages, recordings reflecting the sounds of the Earth, and the ultimate 1977 mixtape featuring 90 minutes of music from Beethoven to Chuck Berry. Sagan wanted the Beatles' Here Comes the Sun on the disc, but EMI refused copyright permission for the universe. I like to imagine that Carl Sagan put the song on the record anyway in a great cosmic two-fingered salute to corporate Earth. That would have been pure Sagan. You're most welcome to go fetch it. The outside cover of the golden disc is more functional. As well as instructions on how to play back the images and sounds at precisely 16 2/3 revolutions per minute for the audio, and how to build a record player, it also contains a map, so that any extraterrestrial civilization will be able to trace the record back to our planet. The map uses the position of 14 pulsars whose precise locations are marked relative to the Sun. The pulsars are identified by their fingerprints. Each has a unique and unvarying rate of rotation. The most important piece of content on the cover is the key to unlock the information, a diagram illustrating the spin configurations of a hydrogen atom. The 21-centimeter hydrogen emission line is a fundamental and universal property of nature, a Rosetta Stone that will allow an alien scientist to unlock the secrets of Earth. The disk also contains one last invisible source of information. Electroplated onto the surface of the cover is an ultra-pure sample of uranium-238, an isotope with a half-life of 4.468 billion years. This is Voyager's clock, a way for any civilization to determine the age of the record, assuming that they aren't creationists who disagree with radiometric dating. Perhaps these are the sort of aliens that would also be offended by nudity. For all the thought and care that went into these disks, neither Voyager spacecraft is heading towards any particular star. These tiny craft constructed by human hands will almost certainly never be found. The vastness of space swallows travelers, and of course Voyager's scientists and engineers knew this. That, however, is not the point. The act of launching these gilded emissaries into space expresses something important. It's my childhood science fiction dream of living in a Star Wars galaxy filled with life and possibilities. It is a desire to reach out to others, to attempt contact, even when the chances are vanishingly small, a wish not to be alone. The golden discs are futile and yet filled with hope, the hope that we may one day know the boundaries of our loneliness and lay to rest the unsettling internal noise that accompanies the enduring silence. Friends of space, how are you all? Have you eaten yet? Come visit us if you have time. Margaret Suk Ching, Voyager Golden Record. Alien Worlds. Let us now return to Frank Drake's equation and use it as intended as a framework to address in a systematic manner the question of our solitude. Recall that the equation consists of a series of terms which, when multiplied together, give an estimate of the number of currently contactable civilizations in the Milky Way galaxy. At the 1961 Green Bank meeting, only the first term, the rate of star formation in the Milky Way, was known with any precision. Over half a century later, we can do much better. The next term in the equation is the fraction of stars in the Milky Way that have planets orbiting around them, most definitely a prerequisite for an intelligent civilization to emerge. It's true that the civilization may not have remained confined to its home world, and we will discuss this possibility later on, but it must be true that for life to emerge and evolve to the point where it can build spacecraft, a planet of some sort is required. This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own. Giordano Bruno, 1584. The existence of alien worlds has been speculated about for many centuries. Ever since Copernicus began the process of demoting our solar system from its preferred place in the cosmos, it has been natural to assume that at least some of the stars in the sky must have planetary systems. Yet despite this seemingly common-sense conclusion, reached by virtually every right-thinking astronomer from Giordano Bruno onwards, the existence of other planets remained nothing more than an educated guess well into my lifetime. The vast distances between the stars and the limitations of technology locked us inside our own solar system with no way of seeing beyond. Throughout the 19th century, a number of astronomers claimed to have detected distant planets, but all these observations proved to be flawed. Today, the picture couldn't be more different. The night sky is known to be awash with worlds. One of the more enticing of the known solar systems is located around a slightly smaller, cooler version of our Sun called Kepler-62. Around 1,200 light-years from Earth in the constellation of Lyra, the system has been widely studied because it has at least 5 planets. 2 of them, Kepler-62e and Kepler-62f, are particularly interesting because they are Earth-like in both size and distance from the star. Bathed in Kepler-62 shine, these worlds may, if they have the right atmospheric conditions, support oceans of liquid water on their surfaces. We will discuss the significance of this in the context of life later on. The discovery of extrasolar planets has been possible due to the rapid development of precision astronomical instruments, both space-based and terrestrial, that allow us to see beyond the bright glare of stars to the worlds that lie in the shadows. Imagine looking at our solar system from the nearest star system to Earth, Alpha Centauri. The system is 4.37 light-years away and consists of 2 sun-like stars, one slightly more massive than the other, orbiting each other with a period of approximately 80 years. The red dwarf Proxima Centauri is probably a distant, gravitationally bound component of the system, making it a loosely bound triple star. Looking back towards Earth from 40 trillion kilometers with the naked eye, our Sun would look like any other solitary star. Detecting exoplanets is no easy task because planets are vanishingly small and faint, masked by the brightness of their parent stars, and directly imaging them remains a major technical challenge. To step out of the glare has required the development of indirect methods of detection based on surprisingly sensitive technologies. On the 21st of April 1992, the first conclusive detection of an exoplanet was made by radio astronomers Alexander Vorschan and Dale Frail, working at the Arecibo Observatory in Puerto Rico. They were hunting for planets around a pulsar known as PSR 1257+12, located 1,000 light-years from Earth, using a delicate method of indirect observation known as pulsar timing. Pulsars are spinning neutron stars, some of the most exotic objects in the universe. PSR 1257+12 is 50% more massive than our Sun, but has a radius of just over 10 kilometers. It is, in effect, a giant atomic nucleus, spinning on its axis every 0.006219 seconds. That's 9,650 RPM. As you may gather from this rather precise statement, it's possible to measure the spin rates of pulsars with great precision by timing the interval between pulses of radio waves emitted from the stars like a lighthouse. Volschan and Frail reasoned that if a large enough planet was orbiting a pulsar, the gravitational tug should shift the arrival times of the radio pulses by enough to be detectable.